Okay, now we're going to talk about atomic spectra. And atomic spectra is basically a way of detecting different types of atoms, and it uses the properties of light as a particle to do this. And it has a lot of really important applications in chemistry, in astronomy, and in material science. So we're going to look at how exactly this is done, how it provides energy of the quantization of energy in atoms. So basically, why there's only discrete amounts of energy in atoms, and we're going to figure out how to calculate the wavelengths of these lines, as we can see in this graph right here. Okay, so the spectrum of light. This is an example from a famous 1973 album cover, and this right here is a prism. So we've probably all seen examples of this where a bright white light shines through the prism, and what happens is that light gets refracted and it gets broken into its constituent colors or its component colors. So each of these wavelengths of light, each of these colors, has a different amount of refraction. So because they're all different wavelengths, they all refract differently through the prism, and that's why they get broken up into their component colors, as we can see in this picture. Now, each of these individual lines corresponds to a color of light that's emitted by a specific atom. Okay, and as we can see in the graph below, it shows the intensity of that light that is emitted for a certain wavelength. Okay, so we see little spikes at each of these points, and that is where light is emitted from an atom. Now, why is light spontaneously emitted from an atom, and why is it not continuous like a white light was? So why is it only emitted at specific wavelengths? So this is the reason right here. So let's say that a photon comes into an atom, so a photon of light. So it's giving a specific amount of energy. Now, photons only have discrete amounts of energy. So a photon comes into the atom, an electron is going to absorb that amount of light. Okay, so right here, an electron absorbs the photon, it goes up an energy level. So an electron in this little area right here, let's say n equals 2, it has a specific energy. Now when that electron absorbs a photon, it jumps up in energy, so it moves up to an excited state, so it gains energy. Meanwhile, it gains that energy. Now what it wants to be in is in the ground state. So here's an electron in the ground state, n equals 1. Okay, so that's the lowest energy possible, and it's kind of like how objects want to have the minimum energy possible. So if you have a ball on a hill, it's going to want to roll down that hill. It wants to have the minimum energy possible, and that's what electrons are like. Okay, as we can see here, this green little thingamabob is the nucleus. So what happens if our petty electron here goes to the energy level n equals 3, and what happens there is it emits a photon. Okay, and that's where we saw in the previous slide why certain lights are emitted, because that's what's happening here. An electron has a certain amount of energy. It spits out some of that energy in the form of a photon. The electron emitting the photon goes down an energy level. So it emits that energy. Whatever energy is left moves down to that energy level. So electrons can only have specific energies that correspond to n equals 1, n equals 2, n equals 3, etc., etc., etc. It can't have any possible energy. It is limited by what energies it can have. Now, this is just an illustrative picture. Note that this isn't exactly what an electron looks like. It's not exactly like the solar system model you were all taught in your younger years. Okay? So here is what it looks like. And these are the different energy levels n. Here are the jumps in energy levels. So, for example, this one right here is jumping from a state n equals 2 to n equals 1, which, if we go back, is right here. So n equals goes from the first to n equals 1. So an electron jumping from between those two energy levels. Okay. Each of these, so from 2, 3, 4, 5, 6, all of those jumping down to the first energy level, is what's known as the Lyman series. Okay, it's named after a scientist named Lyman who basically first discovered this, and all of these are emitted as ultraviolet light. Whereas the Balmer series, which is a bit more interesting, shows not going to the ground state, but in general going from 3 to 2, 4 to 2, going to the second ground state. and the Paschen series goes to the third ground state. Now, you can see that there's a number of different ways that electrons can move to the ground state. So it can go 2 to 1, or for example, if it's in the third energy state, it can go 3 to 1, or it could do in the Balmer series, could go 3 to 2, and then could go 2 to 1. Okay, so there's a number of different combinations and different ways that it can jump from high energy levels to low energy levels. And this atom we're looking at right here is hydrogen. So this is the energy levels of hydrogen with some of the transmissions. So there's a whole bunch of transmissions it has. This is some of them. Each atom has its own distinct energy level. So hydrogen, this is a pretty well-known number. This is, if any of these numbers, you should know this one. The ground state is minus 13.6 electron volts. Okay, so that's how much energy is essentially contained by the ground state. And when it absorbs energy, it moves up to a different energy, so minus 3.4, for example. And it continues moving up when it gets to ground states until it gets to this point here. Now, once it at a state of n equals infinity, or 0 electron volts, that means it has exited the atom. It's no longer part of the atom. And that is what's called ionization. So that electron is ionized. Okay, so each of these... Oh, there we go. Oh, going back. Uh-oh. No. Okay, technical difficulties over. So this energy level... So as you can see, the energy levels correspond with our little primitive diagram of the atom. Okay, now, how do we know, in the Balmer series, for example, how do we know what these colors are going to be? How do we know that this is going to emit infrared light? How do we know that the Lyman series is going to emit ultraviolet light? How do we know these things? Well, we know what energy corresponds to each different energy level. And we also know this handy equation. E equals H F. The pen is being sensitive today for some reason. So, we know that that energy is given by Planck's constant times the frequency of light emitted. So if we know the energy between two different states, we know Planck's constant, we can find the frequency. And from the frequency, we can find other important quantities. For example, we know, since this is light being emitted, that the speed of light is equal to lambda times the frequency. Okay, so speed of light equals the wavelength times the frequency. So if we wanted to find, for example, for the Balmer series from 3 to 2, find what wavelength that is, we would go the energy from 3 minus the energy from the second one. I apologize for the poor writing. I seem to be having some difficulties with my pad. So this is equal to H F. Okay, if you rearrange this for frequency, you can find it in terms of wavelength. So you just put in these two numbers, which are minus 1.51, minus 3.4, and you can just solve for the wavelength. Okay, so that's how you find frequencies of light. And this can be applied in, for example, here's one cool application that I've decided to outline. There's a number of different ways, but I think this one's pretty cool. How light from a star goes through a planet. So it gets, basically, the light is going through the planet's atmosphere. On Earth, we detect it using a spectrograph. So we can look at the star's light, see a spectrograph, And what we're basically going to do is compare what the spectrum of the star looks like with and without the star and without the planet in front of it. And what we can actually see is that some of that light is absorbed in the atmosphere by the type of elements that are contained within the atmosphere. And here, this is the line we get. So we can get a full spectrum from the star, except for these two little lines right here. What this means is that that light is absorbed by atoms in this planet's atmosphere. And we know because every single atom, so every single atom that exists, has its own characteristic spectra. And so if we just compare this absorption spectra with a spectra of a different atom, or any of the atoms, we can see that it matches exactly that of sodium. So we know that sodium is contained within this atmosphere. So that's one of the cool examples of using atomic spectra to discover the atmospheric composition of different planets. Okay, so to summarize, atomic spectra is good evidence that there are discrete energy levels in atoms. It also gives direct evidence of the photon nature of light. And it has also cool applications for the emission spectra, where light is emitted, and the absorption spectra, where light is absorbed by an atom. Okay, hopefully that was helpful.